Welcome to another video lecture, and this video lecture is about infinite series of real numbers. To motivate us in this lesson, let's consider first a sequence of real numbers a sub n. So we have the first term a sub 1, second term a sub 2, third term a sub 3, and so on. So this list is infinite and it is ordered. So the questions that we are going to answer today is this. What does it mean to add all the terms, all? So we need to say we are adding infinitely many, a collection of infinitely many numbers. And what do you mean by the sum of all these real numbers? Is it possible to add an infinite collection of real numbers? So in this lecture, we are trying to answer these questions, and we would like to know if this makes sense. So what will be our most sensible definition? To give you an idea about infinite series or a sum of an infinite sequence, let's consider this infinite sum. Let's call it sum with quotation sum. We are adding 1/2 plus 1/4 plus 1/8 plus 1 over 16 plus 1 over 32 plus and so on. So here you see the pattern is that every term is, well, 1/2 of the preceding term. So if you take half of 1, you get 1/2. If you take half of 1/2, you get 1/4. If you take half of 1/4, you get 1/8, and so on. So you can think of 1 as the area of a unit square, so that 1/2 will be the area of 1/2 that square. If you take 1/2 of this 1/2 square, you get a 1/4 square, and so on. We continue in this fashion. If you add 1/8, you add 1 over 16, 1 over 32, and so on. You see that if this pattern continues forever, then although we cannot fill in the gap or the remaining gap using a finite number of steps, but after infinitely many steps, you see that this will eventually be filled. Let's agree on that. So therefore it makes sense to say that this sum equals 2, because after all the terms you get an area of 2. Okay, so this is our formal definition. So we start with a sequence of real numbers a sub n. So the infinite series, usually denoted like this, is defined to be a sequence. So a series is just again another type of sequence. A sequence whose nth term is s sub n, and s sub n is defined to be the sum of the first n terms. Notice that this sum is well defined because this is a finite sum. So meaning to say we understand every term of s sub n, or every term s sub n for n greater than or equal to 1. This is why we call s sub n the nth partial sum. Now we say that this infinite series, or sometimes if I want to be lazy, I drop the indices. Automatic, kapag sinulat kong ganito, it refers to the infinite sum. Now because an infinite series is not really a sum, it's a sequence, we say that this series converges to a sum S if the sequence S sub n of partial sums converges to S. Meaning to say, if the sequence defined by this converges to a limit S, then we say that the sum is convergent. Verb form converges. Otherwise, we say that the series diverges. So let's consider some examples. Okay, the series is the summation of 2 over n times n plus 1. N runs from 1 to infinity. So if we list down the terms of this series, we get 2 times 1 times 2 plus 2 times 2 times 3 plus 2 over 3 times 4 plus and so on. So we don't like to simplify terms, so for us to see the pattern. Okay? So the question is, does this converge? Well, the only thing that can answer this question is the nth partial sum. So as you can see, the nth partial sum of this series is this. This is the first term, the second term, this is the nth term. Does this converge to anything? How do we know? Well, observe that for each k, this expression, no, can be rewritten as 1 over k minus 1 over k plus 1 as its partial fraction decomposition. Therefore, 2 over k times k plus 1 can be re-expressed as 2 over k minus 2 over k plus 1. Thus, each term here may be re-expressed as shown. Itong 2 over 1 times 2 can be expressed as this. Ito naman magiging ganito, ito magiging ganito. As you can see, these things cancel. Okay? What we're left here is 2 minus 2 over n plus 1. So we get a closed form for s of n, namely 2 minus 2 over n plus 1. As n approaches infinity, we know that 2 over n plus 1 simply goes to 0. And hence, the sequence of partial sums converges to the sum of 2. Therefore, the infinite series converges and its sum is equal to 2. How about the sum? Summation -1 raised to n plus 1 and from 1 to infinity. As you can see, when n is 1, you get 1. When n is 2, you get -1, and so on. As you can see, the signs alternate, but the values are all 1. That's why sometimes instead of writing 1 plus minus 1 plus 1 plus minus 1, we just remove the parentheses and write it as 1 minus 1 plus 1 minus 1 and so on. So the question is, what is the sum of this infinite series? Well, somebody says that the sum is equal to 0 because if you try to group terms like this, you get 0 plus 0 plus 0 plus 0 plus 0 and so on. Some others say that the sum is 1. It is because if you group terms like this, no? If you see terms like this, you get 1 plus 0 plus 0 plus 0 plus 0. So the sum is 1. But some others say that the sum is 1/2. For example, if you denote by s the sum, okay, you subtract 1, you will get this. Okay, then you multiply -1 on both sides, you get this. But as you can see, the right hand side becomes the same s. So therefore 1 minus s is s, or 2s is equal to 1, therefore s is 1/2. So which one is correct? Is the sum really 0, 1, or 1/2? It turns out that the answer is neither among those choices. Because in the first place, does the sum really exist? Or does the series converge? If you look at the nth partial sum, the first partial sum is of course 1. If you remove every term and leave the first term, you get a 1. If you remove everything except for the first two terms, you get a 0. If you remove everything except for the first three terms, you get another 1. So as you can see, the pattern goes like this. The nth partial sum is 1 if n is odd, and 0 if n is even. Because we know that this series has two limit points, mean to say, a subsequence of this converges to 1 and a subsequence converges to 0, and the smallest limit points, or the limit inferior of s of n, is 0 and the limit superior of s of n is 1, and they are not equal. It only means to say that the series diverges, or you can say that a subsequence converges to 1 or a subsequence converges to 0. When that happens, the sequence does not have a limit, because if a sequence converges, every subsequence must converge to the same number. Therefore, the correct answer is that this series is divergent and it has no sum. It cannot have a sum. So all those algebraic arguments are technically wrong in the first place. So as you can see, before answering what is the sum of a series, we first need to ask whether it has a sum or not, or if it really converges or not. That's the more important thing. In fact, in most of the situations that, in most of the cases that we will be interested in, what matters is that we were able to prove that the series is convergent and without regard to whatever the sum is. In other words, without knowing what the real sum is, how can we show that the series is convergent, or how can we know in advance if the series doesn't have a sum at all? The first thing we need to do is to establish some nice examples. The next example is important because most of the examples will be compared to this one. The following series is what we call as a geometric series. So the series starts with some number a, and every time we multiply a fixed constant r that is not equal to 1 to get the next term. So we start at a, we multiply r, we get a times r. Then we multiply r again, we get ar squared, and so on. Just like the first series in this video. The series 1 plus 1 half plus 1 third plus 1 fourth plus 1 eighth, and 1 plus 1 half plus 1 fourth plus 1 eighth plus and so on is an example of such a series. In that case, a is 1 and r is 1 half. This infinite series is sometimes called, or commonly known as, the geometric series, or the infinite geometric series if you wish to call it that way. Notice that the end partial sum of a geometric series is quite special because it has a closed form. When you say closed form, it doesn't use the dot 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 or the and so on symbol. If you add all of this, the first n terms, you can factor a and get this one. Now algebraically, if you multiply 1 minus r by 1 plus r squared plus and so on, you get 1 minus rn. Hence, because r is not 1, we can divide both sides by 1 minus r. And therefore, we get the following identity. To answer the question in this example, we would like to know, when does this sequence converge? Okay, so as you can see, the sequence will converge if and only if r to the n converges. The sequence r to the n converges. And from advanced calculus 1, we know that this converges if and only if the absolute value of r is less than 1. Meaning to say the magnitude is small. Because if r is, let's say, 2 to the n simply diverges to infinity. If r is 1 half, r to the n, or 1 half to the n, simply converges down to 0. So, therefore, the end partial sum will converge if and only if the magnitude of r, or the absolute value of r, is less than 1. Hence, the infinite series or the geometric series converges if and only if ang tawag natin dito sa r, yung common ratio, is less than 1. In particular, if the common ratio r has a magnitude less than 1, we know that r to the n converges down to 0. This is why, in this case, if this converges down to 0, this will converge to a over 1 minus r as the infinite sum. So, pakakatandaan, ito'y importante, ito'y paulit-ulit na ginagawa. The geometric sum, or the infinite geometric series, has a sum a over 1 minus r precisely when the absolute value of r is less than 1. Okay? So, the first theorem is about linearity. It only says that if you have two infinite series which are both convergent, and then adding the terms adding the series term by term or term-wise addition, you get a new sum which is also convergent. For example, it says that if, let's say, A1, A2, and so on, or A3, dagdagan natin na isa. Let's say this one is convergent. Let's say the sum is S1. Let's say, and I have another series. Okay, let's say B. And then let's say the sum is S2. If you add this term by term, so I get a new number A1 plus B1. I get another number A2 plus B2, and so on, A3 plus B3, and so on. What I get is another infinite series, which is again convergent. In fact, the sum of this is equal to the original sums, S1 plus S2. Now, how do we prove this theorem? So, in this proof, I will just be doing this part and this part, no, and then the other part is left as an exercise. Okay, so to prove this, let's call S sub n, and let's denote by S sub n and T sub n be the n partial sum of the series A, sum an and sum bn respectively. So si S sub n yung n partial sum ni summation an, si T sub n yung n partial sum ni summation bn. Then because we know that this series converges, then these two sequences converges. So we can say that S sub n converges to S and T sub n converges to T for some S and T, which are real numbers. We then consider the n partial sum of summation quantity an plus bn. So if I denote that by let's say u sub n is a1 plus b1 plus a2 plus b2 plus and so on, an plus bn. But this sum is finite, therefore the rules of algebra apply. I can use associativity and commutativity. So I can group all the, in other words, I can group all the a's and I can group all the b's together. And as you can see by definition, this is S sub n and this is T sub n. Therefore, what's the limit of U sub n? It's the sum of two convergent sequences. So the limit of the sum is the sum of the limits. So this is S plus T. In other words, as a conclusion, yung U sub n, which is the n partial sum of this infinite series, right, converges to S plus T. But S is the sum of the summation an and T is the sum of the summation bn. So therefore, we get to have the following. Okay, so that's the proof. Let's consider this example. Show that this series converges, and what is the sum? Okay, so at first this looks very intimidating because of its nature, right? Correct? Okay, so the thing that we need to do here is to simplify the expression or the nth term of the series. Okay, so notice that I can rewrite this as 3 times 2/5 raised to n plus 2 times 3/5 raised to n. Okay, since summation 2/5 to the n from 1 to infinity, and summation 3/5 to the n are geometric series. We can argue that they are geometric series with ratios less than 1, no? Actually positive, no? And greater than 0. Then they are convergent. So by linearity, a linear combination of these two infinite series must also converge. Yung summation n from 1 to infinity ng 3 times 2 to the n plus 2 times 3 to the n over 5 to the n must also converge. Ang tanong, to which sum? Well, according to linearity, this is nothing but what? This is nothing but 3 times the summation or the sum 2/5 to the n plus 2 times the summation n equals 1 3/5 to the n. Okay? If we try to expand, no? This is 2/5 plus 2/5 squared plus 2/5 cubed and so on, plus 2 times 3/5 plus 3/5 squared and so on. So, the formula for an convergent infinite geometric series is that the first term divided by 1 minus the ratio, and the ratio here is also 2/5 plus 2 times the first term divided by 1 minus the ratio 3/5. So if we simplify, this is 3, multiply tayo ng 5 on both numerator and denominator, you get 2 over 5 minus 2 plus 2 times 3 over 5 minus 3. So, what will happen? Magka-cancel ito. So, the sum is 5. Okay? That's it. Another. For what value or values of x is this infinite series convergent? Although it may not look like one, this infinite series is actually geometric. No? You can write this as follows. You can write this as 2 times x plus 3 raised to n. And when this one is expanded, this is 1 plus 2 times x plus 3 plus 2 times x plus 3 squared, and so on. Right? So remember, an infinite geometric series converges if and only if the ratio has an absolute value less than 1. So this will converge if and only if the absolute value of 2 times x plus 3 is less than 1. Now we just solve for this inequality. Less than 1. When will this happen? This will happen precisely when this is true. Okay? Subtract 3. How do we subtract 3? Negative 2 over here, negative 4 right there. Is that correct? Yeah, I think so. Divide by 2 or multiply by 1/2. Negative 2, negative 1. Okay, so therefore, converges, lagyan natin the series, converges if and only if x is between negative 2 and negative 1. So let's have the first theorem of this lecture. It says that if you have a convergent series, then necessarily the nth term of the series cannot be something that gets larger and larger. It should converge down to 0. Right? Do you get that? So for the proof is kind of easy. So for example, the sum is S. Because the series is convergent, it has a sum S. So if S sub n is the nth partial sum, then we know from definition that S sub n must converge to S as a sequence. Thus, if we look at the limit of A sub n, take note that A sub n can be obtained by subtracting the first n minus 1 terms from the first n terms. So imagine I have n terms right here, the first n terms. These are the first n terms. At ito yung S sub n. Of course, the first n minus 1 terms is S sub n minus 1. So if I subtract S sub n minus S sub n minus 1, I get A sub n. But the limit of this is the limit, because this is a sum, no? Limit of S sub n is S. And the limit of S sub n minus 1 is also S, because S sub n minus 1 is just a, well, you can consider it as a subsequence. It's just one term behind S sub n. So, kung saan pupunta yung S sub n, dun din naman pupunta yung S sub n minus 1 pag nakarating na ng infinity si n. So, the limit is S minus S or 0. So, that's very easy. Now, what really is important in this theorem is not the theorem itself, but actually the contrapositive. If one finds that the limit of A sub n is not 0, then you can conclude that the series is divergent. This is why this is what we call as the divergence test, because as a conclusion, one concludes that the sum is divergent if the limit of the n term is not 0. For example, when you look at the intimidating series summation of cosine 1 over n from 1 to infinity, notice that if you take the limit of the nth term, the limit of the cosine 1 over n is cosine of 0, because 1 over n goes to 0, and that's 1. Because 1 is not 0, then you can say right away that the series is divergent. The question is, if an converges down to 0, does that mean that the series is convergent? What do you think? Well, it turned out that the answer is no. One counterexample is this. We call this as the harmonic series. This is the sum of the reciprocals of the natural numbers. 1 plus 1 half plus 1 third. Or more briefly, we can write this as a summation of 1 over n from 1 to infinity. Notice that, of course, the limit of 1 over n is 0. First, I want to show that this is divergent. Let's observe that S sub 2 is actually 1 plus 1 half. Take note, S sub n denotes the nth partial sum. No, I don't like S sub 3 or the third partial sum. I just need to get S sub 4. Because here I can group the last two terms, 1/3 and 1/4, like so. Now, of course, between 1/3 and 1/4, 1/4 is smaller. So if I'm going to replace 1/3 by 1/4, so I get now 1/4 plus 1/4, the sum will decrease. If 1/3 was replaced by 1/4, I get 1 plus 1 half plus 1/4 plus 1/4. These two 1/4s will become another half. So this is 1 plus 2 times 1 half. Now, I would like you to look at the pattern, huh? And then next, I'm going to look at the 8 partial sum. So here are the first 8 terms of the infinite series. And ito siya. 1 plus 1 half. You group ko yung third and fourth terms. Then you group ko yung last 4 terms. Again, between 1/3 and 1/4, 1/4 is smaller. So if I replace 1/3 by 1/4, I get a smaller sum. And then among 1/5, 1/6, 1/7, and 1/8, 1/8 is the smallest. So if I replace 1/5, 1/6, and 1/7 by 1/8, I get a smaller sum. So I will do that. I will replace 1/3 by 1/4, and this 3 will be replaced by 1/8. I now get 1 plus 1 half plus 1 half plus 1 half. So therefore, I get a sum that is greater than 1 plus 3 times 1 half. So this is a lower bound. Okay. Continuing in this fashion, or by induction, one can prove that S sub 2 to the k, ang susunod dito S sub 16 eh. I-group mo naman yung 1 over 9 hanggang 1 over 16. Like so. Magiging mas malaki yun sa 1 plus 4 times 1 half. In general, S sub 2 to the k, so the pattern of this is 2 to the k, right? Is greater than 1 plus k over 2. But 1 plus k over 2 as k approaches infinity simply goes to infinity, right? Because S2k is even bigger, then of course by comparison, you can also conclude that S2k must diverge to infinity as k approaches infinity. Because the sequence is strictly increasing, palaki to ng palaki, no? And this subsequence is diverging to infinity, then we can conclude that the sequence itself is diverging to infinity. And therefore, we say that the sum is divergent and it has no sum. In fact, sometimes or we roughly say that the sum is infinity just because the n partial sum grows without bound. Okay? As an illustration, this is the summation or the sum of all 1 over n, and from 1 to infinity, ito yung 1, 1 half, 1 third, 1 fourth, 1 fifth. So as you can see, even though the terms that we add are getting smaller and smaller, no? Getting smaller and smaller, what? We get an infinite sum. This is why this example is counterintuitive. So for example, when you say that the sum is infinity, it means to say that if you give any number m, no, for each m, that for any positive m that you will give, there will always exist an n such that the sum of the first n terms will be bigger than m. There will always come a time that the n partial sum will exceed m for any candidate m that you will give. For example, in the case of the harmonic series, when do you think will the sum exceed 100? Medyo matagal kasi ang dinadagdag mo na dinadagdag ay lumiliit na lumiliit. So, habang tumatagal, it gets harder to get to 100. But because we have proven that the sum is infinity, it will eventually exceed 100. In fact, no, meron tayo kasi estimate eh. S2 to the k is greater than 1 plus k over 2, right? So, kailan to lalagpas ng 100? Let's say, for what value of k? So, tingnan natin yung inequality na to. Well, k over 2 is greater than 99. So, k should be taken to be greater than 198. Is this correct? Okay? So, ibig sabihin, if k is 199, no? Sure ako ng s sub 2 to the 199 will be greater than 100. So, it will take me 2 raised to 199 terms to get a sum, a partial sum, which is greater than 100. So, ganun kabagal. Ang laki no? 2 raised to 199. Ganun kabagal mag-increase yung series na ito, but then it manages to get to infinity. This is why this example is really important in analysis because it's counterintuitive. Yet, as you can see over here, alala nyo to yung 1 half, 1 plus 1 half plus 1 fourth, it can be written in this manner. No? Ito naman, this manages to get a sum of 2, whereas ito ay naging infinity. Ano nangyari? Bakit ito finite ang sum, pero bakit ito infinite ang sum? Now, if you compare the two graphs, as you can tell, no, itong blue series natin goes down to 0 faster, no, than the red series. So the next question will be, how fast should my nth term be going to 0 in order for the sum to be finite? So we shall answer this question in the next few lessons. So, more or less, in our future discussions, um, most of the infinite series that you will encounter in analysis uh, can be shown to be convergent, but it's very hard to know the sum. No? The question is, kasi by definition, you have to prove that the nth partial sum converges to a limit to say that a series is convergent. So we ask, can we know the convergence of the series without having to know the sum? Because the sum is very hard. You know that limits can be very hard to find at times. Okay? This is why we have Cauchy to the rescue. Remember, our replacement for the existence of limit is to prove that a sequence of real numbers is a Cauchy sequence. We call this the Cauchy's criterion for convergent sequences of real numbers. Although this works or this holds only for real numbers, or for any kind of set that is complete, or in any space that is complete. Recall that a sequence x sub n of real numbers converges if and only if it is a Cauchy sequence. Now, what is a Cauchy sequence? This is what we mean by that. Real numbers, Kasi, for example, if you replace this by rational numbers only, if you restrict this to rational numbers only, this is not true. This if and only if statement is not really if and only if. Ano ba ibig sabihin ng Cauchy? Pag sinabing Cauchy, for every epsilon greater than 0, a natural number n can be found so that two terms whose subscripts are bigger than n have distance less than epsilon. Meaning to say, if two terms have very big subscripts, then their distance to one another is getting small. Meaning to say, as n passes or as time passes, the terms are getting closer to one another. That's what we mean by a Cauchy sequence. Of course, it is natural to conclude that if a sequence is convergent, it's naturally Cauchy. Because if a sequence is convergent, every term clusters, the terms of the sequence clusters to a particular point, parang ganito. So, parang nagka-cluster sila dyan. And of course, as they cluster to a single point, as they get nearer to a point, then together or among themselves, they are getting closer to each other. That's why convergent sequence is a Cauchy sequence. But the converse of this is not always true, especially when the space is not the real number line. So, for example, I can give you, or in analysis, in advanced calculus, you have seen Cauchy sequence of rational numbers that doesn't converge to a rational number. But for real numbers, the converse can also be said. Once you have proven that a sequence is Cauchy, then you can conclude that it is convergent. Gumamit kayo sa proof nito, gumamit ng Bolzano-Weierstrass theorem if you can remember. Okay? So therefore, if S sub n is the nth partial sum of the infinite series summation an, then by definition, this series is convergent if and only if this sequence is convergent. If and only if this sequence is a Cauchy sequence. Now, ano bang meaning ng S sub n? Ang meaning ng S sub n is a sub 1 plus a sub 2 plus and so on, a sub n. Now, question, how does this condition convert to infinite series kung ito yung meaning ng S sub n? Papalitan yung x sub n ng S sub n. Ito siya. This is why we have the following, or the so-called Cauchy's criterion for convergence of infinite series of real numbers. So, the infinite series of real numbers, summation an, converges regardless of the sum. We normally don't know the sum, what the sum is, if and only if the sequence of partial sum is Cauchy. And by that, we mean for every epsilon greater than 0, an n can be found so that this expression is less than epsilon whenever m exceeds n and they both exceed big N. So, why does the cushiness convert into this? Kasi, kung let's say si M at si N parehas malaki kay N, sabihin na lang natin na si N, M na lang yung mas malaki kay N. Kasi kung compute mo yung S sub M minus S sub N ito yung less than epsilon, di ba? Di ba? Kanya kapag cushy. Yung S sub M kasi, ito yung A sub 1, A sub 2, A sub M. Pero syempre, dahil mas malaki si M kay N, dadaanan dito yung A sub N. Right? So, ito yung S sub M. Isusubtract mo ngayon yung A sub N. Anong may iwanan? Ano yung may iwanan? Ang may iwanan mula AN plus 1, AN plus 2 hanggang AM. Therefore, the following theorem. In the next video lectures, makikita nyo kung paano gagamitin yung Cauchy's criteria na ito to prove other results or establish other tests, how to know if a series is convergent or not. No? More particularly, ganito yung magiging discussion natin. No? Mag-start muna tayo sa series with non-negative terms. Ito muna yung pag-aaralan natin in the next video lesson. Kasi kapag ang mga terms ng series mo ay non-negative lahat, the series kind of well behaved. So, very predictable yung kanyang behavior. Kasi if all the terms are non-negative, ang mangyayari, yung S sub n natin, yung sequence of partial sums natin is just increasing. And you know that if an increase, to know whether an increasing sequence is convergent, you only need to prove that it is bounded above. So it's quite easier. So that's a basic fact. We call that as the monotone convergence theorem. And then we will study series with negative terms and study the so-called absolute convergence. That, ito yung exciting dito eh. Kapag ang series may negative terms, the series kind of disobeys some laws of algebra. Meaning to say, kapag may mga negative terms na, hindi pala pwedeng basta-basta ka gumamit ng mga commutative property or associative property. You cannot regroup terms because sometimes the sum of the infinite series might change. Or the sum is affected by a rearrangement of the terms. Pag-uusapan natin yun. Pero yung tinatawag nating absolutely convergent series, kapag ang series ay absolutely convergent, hindi sila sensitive sa rearrangement kahit may mga negative na terms. Okay. Ay identify natin sino-sino yung mga absolutely convergent, sino yung mga hindi. Okay? See you in the next video lesson.